Let me welcome you to this lecture. We have now discussed about the oxides of carbon. That is, mainly we have discussed about two of the oxides of carbon, that is carbon monoxide and carbon dioxide, because these are the most stable oxides of carbon. So we will now discuss about carbonates. So the acid, that is carbonic acid, forms two different series of salts. One is carbonate, that is CO3, two negative ions are present in these salts, and the other one is bicarbonate, that is HCO3 negative. So in case of carbonates, we have group 1 and group 2 metals, as well as divalent metals form carbonates, and these are examples, say calcium carbonate, magnesium carbonate. All these group 2 metals form carbonates, and apart from that also group 1 metals also form carbonate, like sodium carbonate, we know cesium carbonate. All these group 1 metals also form carbonates. Now bicarbonate also we have only for group 1 metals and for ammonium ion. For other metal ions, bicarbonates are not known, only group 1 and ammonium, while for carbonate we have both group 2, group 1, as well as several other transition metals or divalent transition metals also form the carbonate salts. Now one particular aspect that we must notice here is that when we look at the carbonates or oxides of carbon, silicon, and we see that silicon forms an ion SiO4 4 negative, but carbon does not form this sort of an ion, and instead we only encounter CO3 2 negative. Again, similarly, if we go to the other group, or the next group, or the silicon group, we know nitrogen forms this nitrate ion, NO3 negative, and its higher container, that is phosphorus, forms PO4 3 negative. So there is a difference in the kind of oxide that is formed by the lighter elements. What we see, this does not form NO4 3 negative. Say nitrogen does not form NO4 3 negative; it forms NO3 negative. While carbon also does not form CO4 4 negative, and instead we see only CO3 2 negative. While the heavier elements, silicon or phosphorus, can form SiO4 4 negative as well as PO4 3 negative here. There are two reasons for this. The first reason is that because the lighter elements here, carbon and nitrogen, the size of these elements are quite small, and that is why one cannot put 4 oxygen surrounding these smaller atoms, and that is why they are not able to form CO4 4 negative or say NO4 3 negative. This sort of ions cannot be formed. The second reason is because, again, what we see is that these lighter elements, carbon and nitrogen, the valence shell is essentially 2s and 2p orbitals are there, and similarly in case of oxygen also we have 2s and 2p orbitals are present, and that is why these lighter elements are able to form p pi bonds, while such p pi interactions are not possible or unlikely in case of the heavier elements, because here the valence shell is essentially 3s and 3p, while for oxygen we have 2s and 2p orbitals. So the p pi interactions are not, and the energy of these orbitals are not compatible to form p pi interactions, and that is why again we cannot have, or we do not have this sort of ion formation or NO4 two negative ion formation, and instead we see this sort of species where extensive p pi interactions are present. So let us now look at the structure of the carbonate ion. And also try to calculate the bond order of this the CO bonds in the carbonate ion. So the carbonate ion, we already may know, is a planar triangular ion. The carbon atoms in carbonate are all sp2 hybridized, and that is why the bond angle here, or OCO bond angles, are all 120 degree here, because the carbon atoms are all sp2 hybridized here. So, and if we look at the structure, what we will see is that we can draw the structure in this way, where two of the oxygen atom carries negative charge and one of the oxygen atom has a double bond here. We can also write resonance structures here, because this double bond essentially is delocalized over a whole molecule. So we can write it in this way, as well as we can write another resonance structure here in this way. So this is the valence bond description of carbonate ion. We can find out the bond order of the molecule by looking at the molecular orbital picture of this molecule. So let us look at the electronic configuration of carbon here. So we know carbon has 4 electrons in the valence shell, that is 2s and 2p. So we have 2s2 and 2p2. This is the configuration, and when carbon is going to form carbonate ion, what it is going to do is it is going to form sp2 hybridized orbitals, and for that, first what we will have is, so we have the sp2 hybridized orbitals, and 3 of the electrons out of the 4 will occupy these sp2 hybridized orbitals of carbon, and another electron is going to occupy this pz unhybridized pz orbital of carbon. These are the sp2 hybridized orbitals, and now these sp2 hybridized orbitals are going to form sigma bonds with the oxygen atom, and that is how from the oxygen atom it is going to form sigma bonds in this way, and this pz orbital or electron in this pz orbital is essentially going to participate in pi bonding. Now, in order to find out the how this pi bonding happens in carbonate ion, in this sort of polyatomic ions, we need to use a different approach, or in order to find out the bond order, we need to use a different approach here. So we will see how we can do it systematically in this case. So first what we will do is that we will count the total number of valence electron in the species here. So the species here is carbonate. So we will count the total number of valence electrons. So let's count the total number of valence electron. So this is equal to each of the carbon atom contains 4 valence electron, and each of the oxygen atom contains 6 valence electron. So 6 into 3, there are 3 oxygen atoms, plus there are 2 negative charge we see. So we also count those electrons here. So that is going to be equal to 4 plus 18 plus 2. So that is 24 valence electrons are present in carbonate ion. Now what we will do is that we will deduct electrons that are utilized for sigma bonding, as well as electrons which are present as lone pair electrons, or which are non-bonding electrons essentially. So deduct electrons using sigma bonding and electrons present as lone pairs. So we know in case of oxygen, there are two of the electron pairs are going to be present as lone pair of electrons here, and we know there are 3 sigma bonds here in case of carbonate. So for formation of 3 sigma bond, we have to deduct 6 electron. So we have 6 electron from sigma bond, and each of the oxygen atom contain or has 2 lone pair of electrons. There are total 3 electrons, so total 6 lone pair of electrons are present here. So that is going to be equal to 12 lone pair electrons. So which is going to be equal to total 18 electrons we have to deduct from the valence electrons, total valence electrons. So that will give us the number of electrons used in pi bonding. So electrons available for pi bonding is now 24 minus 18. So we take the total valence electron, and from there we deduct the electrons used for sigma bonding and electrons which are present as lone pair of electrons. This will give us the number of electrons available for pi bonding, which is going to be equal to 6 here. So total 6 electrons are available for pi bonding in carbonate ion. Now what we will do, we will look at the number of orbitals available for pi bonding. So in case of carbonate ion, what we see is that the carbon center is sp2 hybridized, and it has an unhybridized p orbital is available in the carbon atom. And if we look at the oxygen electronic configuration, this is the electronic configuration of oxygen. And again, oxygen also uses one of the electron for sigma bonding. So oxygen also has an one electron here is used for sigma bonding. These two electron pairs are present as lone pair of electrons, while this electron in a p orbital, so let's assume it to be 2pz orbital, 2pz orbital, so that it is in good symmetry to form a pi bonding with 2pz unhybridized 2pz orbital present on the carbon atom here. So there is an electron on the oxygen atom, on the oxygen, or 2pz orbital on the oxygen atom, on each of these oxygen atoms essentially. So what we have total, there are 4 orbitals are available for pi bonding. One 2pz orbital on the carbon atom, and on each of these oxygen atom also we have a 2pz orbital. So there are total 4 atomic orbitals which are available for pi bonding, and we have total of 6 electrons which are available for pi bonding. Now what is going to happen is that these 4 atomic orbitals are going to combine together when we have formation of the carbonate ion. These 4 atomic orbitals are going to combine together, and they are going to form 4 molecular orbitals. So what kind of molecular orbitals we have here for carbonate ion? Because we have 4 atomic orbitals, so we have atomic orbital of carbon, and we have 3 atomic orbital of oxygen. So what we have is we have formation of 4 molecular orbitals. One is bonding here. So this contains 1 electron. These also, each of these atomic orbitals also contain 1 electron. So 3 oxygen atoms here. And then we have 2 non-bonding orbitals which are again degenerate in nature. So this is bonding, this is anti-bonding, and this is non-bonding. So we have total 4 molecular orbitals, and we see there are total 6 electrons available for pi bonding. Sorry, we do not have 4 electrons, we have total 6 electrons, so we should not write electrons in this way here. So there are total 6 electrons we need to fill, and we are going to fill electrons in order of the energy of the molecular orbitals from the lowest to the highest, and this is how the electrons are going to be filled in the molecular orbitals. And what we see is that the bonding molecular orbital is going to be occupied by 2 electrons, while the two non-bonding molecular orbitals are also going to be occupied by 2 electrons each. So now we can count the bond order in carbonate ion. So when we calculate the bond order, what we will find is that we will deduct electrons present in bonding molecular orbital from the number of electrons present in anti-bonding molecular orbital, and we divide it by 2 here. So total what we will get, the bond order we will get is equal to 1. So bond order here we will get is equal to 1 because we have 1 pi bond in carbonate ion. Now because we have 3 bonds, we have 3 oxygen atoms here, total pi bond order is equal to 1. So total overall the entire carbonate ion we have 1 pi bond, and for each of these CO linkage, if we want to calculate the bond order, then it is going to be equal to 1 by 3 here. So we have the pi bond order is going to be equal to 1 by 3, and total bond order including the sigma bond is going to be equal to 1.3 essentially 3 or 1 by 3 over here. So that is how we can calculate the bond order in polyatomic species involving pi bond, and similar way we can also calculate the bond order in other polyatomic species involving pi bonds. So for example, if we again take the nitrate ion, if we count the number of electrons, we will find it also has a total 24 valence electrons, and again in this case as well we have total 6 electrons are available for pi bonding, and the nitrate ion also it is isoelectronic with carbonate ion, and that is why it is also isostructural. And again the bond order here also you will find, or the total bond order you will find is equal to 1.33, because here also again we have a similar situation. So we will discuss about other polyatomic ions like azide, or say for example sulfur trioxide, when we discuss about these elements later in this course. Now let us get back to the chemistry of the carbonates. So the carbonates of group 2, they are thermally unstable, and when we heat they decompose. So for example, if we take calcium carbonate and then if we heat it, what happens is that it is going to become calcium oxide and carbon dioxide. It is going to decompose as calcium oxide and carbon dioxide, and the stability of the carbonates increases as we increase the atomic number of the group 2 element, or heavier elements essentially are gives more stable carbonate group 2 carbonates. So in case of the stability increases in this way, so beryllium carbonate, so because beryllium is the lightest, then we have magnesium carbonate, then we have calcium carbonate, strontium carbonate, barium carbonate. In this way the stability is going to increase. So as the element becomes heavier, the stability of the thermal stability of the carbonate or metal carbonate also increases. These carbonates are all, what is stability, solubility, some of these carbonates are soluble and they are colorless in nature. All of these carbonates are whether group 2 or group 1 carbonates, they are all colorless in nature. So let us now go and discuss about carbon disulphide. Because it is an important industrial chemical. Carbon disulphide as such, it is a liquid with a boiling point 46 degree Celsius. It is highly flammable because the ignition point or ignition temperature is only 30 degrees Celsius, and it is again a very highly toxic in nature. Now, one reaction, industrially important reaction where carbon disulphide is used is in the manufacture of viscous rayon. So we will see the reaction involved in where carbon disulphide is essentially used for production of viscous rayon. So carbon disulphide, when it reacts with cellulose in presence of sodium hydroxide, because cellulose has free hydroxyl groups, it reacts with carbon disulphide in this way, and we call this as cellulose xanthate or as cellulose dithiocarpamate. Now, this becomes soluble in or it is soluble in aqueous alkali, and then when we do acidification, what happens is that we can make this cellulose comes out or reprecipitates, and now we can make the cellulose as either fibers or also as thin films, which are known as cellophanes. So we have the fibers essentially are viscous rayon, or this is artificial silk, while the films are known as cellophanes and are again highly useful material. So the preparation of carbon disulphide, if we see one can take methane and then do reaction with sulfur at high temperature, that is around 600 degrees Celsius, using aluminum chloride or silica as the catalyst here, and one can prepare CS2 plus H2S is also formed as a byproduct in this reaction. So this is how one can prepare carbon disulphide, and the structure of carbon disulphide, if we look at again, it is a linear compound, and the structure is similar to the structure of carbon dioxide. So this essentially brings us to the end of this lecture. What we have learned during this lecture, we have discussed about the carbonates. We have seen that there are two series of carbonates. Essentially, one is carbonate salt, and the other one is bicarbonate salt. And we have also discussed about the kind of carbonates that are available, because group 2 metals as well as group 1 metals both form carbonates, but only the bicarbonates are known only for group 1 metals, and except that only ammonium ion form bicarbonate. And then we have discussed about the structure of carbonate ion. We looked at the molecular orbital picture, or we've looked how one can determine the bond order of the pi bond here in case of such polyatomic species involving pi bond. So that is, we discussed, we found that in case of carbonate, the total bond order is bond order for each of these CO linkage is essentially equal to 1.33. And then we have also discussed about the thermal stability of these carbonates. We have seen that as we for heavier elements, the thermal stability of the carbonates increases. And after that, we discussed about carbon disulphide, which is a very important industrial chemical as it is used for production of viscous rayon, and we have seen how the reaction involved in production of viscous rayon, where essentially one can dissolve cellulose by formation of this cellulose xanthate or cellulose dithiocarbamate, which can then be reprecipitated as fibers or as thin films upon acidification, and that is how one can prepare such artificial silk as well as these cellophanes. Then we have also looked at how one can prepare carbon disulphide, that is by reaction of methane with sulfur at high temperature using catalyst. One can prepare carbon disulphide, and then we also discussed about the structure of carbon disulphide, that it is a linear molecule like the carbon dioxide molecule. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.